Okay, so today I want to finish up this section on conformal symmetry, and this will take us on to the next real grappling with conformal field theory for the first time. So we'll talk about quantization, and in particular, we will review the quantization principles that we're familiar with from physics, from mechanics. And then I want to talk about how to think about that composition geometrically in terms of how we slice up space-time into spatial slices. And we'll find that each of these types of slicing, even though physics should be independent of how you slice up space-time, they're sometimes more useful for certain things. So I'm going to tell you three types of slicing. These are what we call foliations of space-time. The three principal foliations of space-time that we use. Canonical quantization involves cutting into space-time into space-like slices, but particular to some time-like direction. Then there's something called light quantization, which involves cutting up space-time into light-like slices. So if you think about each event having a past light cone and a future light cone, you slice up space-time tangential to the light cone. Right? And then for conformal field theory, what we're going to be doing is a type of foliation that's based on slicing up space-time into layers like an onion. So layers of increasing radius. Okay, so this is what's called radial quantization. That's going to take us maybe 2 lectures next week. In fact, it might take us all day of next week's lecture. And so there's a lot that I want to cover in this. Today I just want to tie up some loose ends, identifying the generators of conformal symmetry. We've already done a lot of work in solving the Killing vector, the conformal Killing vector equation. So now we're going to take that conformal Killing vector. We're going to identify conformal generators. We're going to write and show you what algebra those generators close. And then to round off things, I'm going to relate that algebra to the algebra of Lorentz generators, actually 2 dimensions higher. I'm going to show you how we can use that to identify the conformal in 3 dimensions. Okay, so that's what I'm okay, so by way of recollecting what we did last time, the conformal Killing vector dimensions psi alpha was A alpha plus omega alpha beta x beta plus minus lambda x alpha plus x squared beta alpha minus 2 x squared b alpha b dot x alpha. So we solved the Killing vector, the conformal Killing vector equation. And we found that this conformal Killing vector, this particular conformal. So this was a constant D vector. And we've got A, we have D components to this vector. Capital D, the number of space-time the number of space-time directions. This omega alpha beta was a D by D antisymmetric matrix. So there's a half D times D minus 1. Independent numbers that specify this. Lambda was a single number. And this B alpha here, it was also a D vector, the D independent numbers that specify this, giving me a total of a half. So the total of the half, summing all of this together, gives me a half T plus 1 minus plus two independent numbers that characterize this conformal killing method. And that's where I left off the last time, and I didn't really cover any of what was going on. So let's see what each of these corresponds to. So to that end, what we need to do is instead consider the finite version of each of these above transformations by turning off all the other ones we're not interested in, and then we'll see what we can identify. So let's start off with the infinitesimal transformation when we turn off b, lambda, and omega. So infinitesimal transformation corresponding to psi alpha equal to a alpha just corresponds to finite transformation. X alpha going to X alpha plus this constant A alpha, which is the translation in space time. Okay, this is the space time translation. Yeah, and if I turn off A alpha lambda B, then it appears that psi alpha equal to omega alpha beta x beta corresponds to x alpha going to x going to lambda alpha beta x beta. In other words, Lorentz transformations, finite Lorentz transformations. These are Lorentz. And then, of course, together, these two make up Poincare transformations, and this is again essentially the Poincare transformations are part of the conformal transformations. Right? So far, nothing new. The infinitesimal transformation corresponding to turning off B, omega, and A, in other words, lambda, I can absorb the minus sign, lambda x mu alpha corresponds to x alpha going to e to the lambda x alpha. This is dilatations. Corresponds to zooming in or out, depending on size lambda. So far, we've seen these things before: scaling transformations, Lorentz transformations, space-time transformations. What about this beta? Sorry, B. Yeah. So to see what this corresponds to, let's turn on everything else. So the A, omega, and lambdas, and what is it that the infinitesimal transformation psi alpha equal to x squared b alpha minus 2b dot x alpha corresponds to. So it looks unfamiliar. let me show you the mild rearrangement of this percentage in the form. Okay. This is a special performance measure. I told you before that, just recall what we did in the course of the analysis, the performance transformations are not unfamiliar. They're composed of combination of inversions, which are performance transformations, translations, and inversions. Let me show you how this appears in general. So again, what we've done here is not go through this kind of geometric route. It was we wrote down the formal equation that said captured the information about performance transformations. That's what kinetic equations do. We then solved the kinetic equation. We put it into this form. Put it into this form for a reason, because I want it to be off kinetic, that is going to be arm. And now we ended up with this guy, and I want to convince you that this guy is the special performance of it. So to do that, let me rewrite this in a little bit more suggestive way. So the first thing to note is what I mean by x squared here is x mu. Okay. And what I mean by b dot x here is b mu x mu. So now let's take that form and just rearrange them a little. So if I rearrange them a little bit, take this. From psi alpha equal to x mu b alpha minus b mu x alpha all times x mu minus b dot x. Take one of these guys out. X alpha. Now you can see that it's in the form of Lorentz of a Poincare transformation. Why? Because I can identify this thing, which is actually symmetric in mu and alpha, with omega tilde of mu alpha, and this thing I can identify with some lambda tilde. And then it's in the form omega mu alpha x mu minus lambda tilde x alpha. Sorry, not operator, Lorentz must be. Be a scaling potential as well. Sorry, what? There is scaling potential as well. Yeah, that's scaling, yes. Yes. Yeah. But it allows me to read off a finite version of this transformation. So the finite version of this transformation so that x mu equals to x mu plus x squared b mu over 1 plus 2b dot x plus b squared x squared. Okay. And my claim is that in this form, it's clear that this is a composition of inversion, translation, and inversion. Let me show you one. So let's go along with x mu, and we'll make an inversion. And the inversion is then x mu. Inversion is then x mu to 1 over x mu. 1 over x mu, same as x mu over x squared. Multiplied top and bottom by x mu. And then I'll translate by b mu. So that goes from x mu over x squared to x mu over x squared plus b mu. And then I'll make another inversion. Inverting this. So that goes from this guy to 1 over this guy. With x mu over x squared plus b mu over 1 over x squared plus 2b dot x over x squared plus b squared, which you can see is exactly the same as that one. So multiply the numerator and denominator by x. The reason we start off writing things in terms of infinitesimal form, then read off generated transformation. The generated transformation generate the algebras that tells us what the overall structure of what's going on is. Okay. So from the infinitesimal, remember what we're trying to do here is give some representation of these generators. The last time for the Lorentz group, we picked this differential operator realization of the generators. We're going to do exactly the same thing here, and then we're going to, well, you'll see your tutorial. And in the tutorial, one of the things that I ask you to do is figure out the algebra. So I'm right now with the algebras. So from the infinitesimal generators, from the infinitesimal form of the possibility vectors, we got generators. Generators. They are the following. And we have P mu is defined d by dx mu, dx by d. M mu is the antisymmetric combination minus I x mu d mu minus x mu d. They're a little confusing because d will appear as both the generator as well as the normal space-time dimension. This is I x dot d. Then we use the story of the conformal transformation minus I times minus 2 x mu x dot d plus x squared x dot x d. Okay. So. And these are the generators of conformal. Given these generators, the conformal group, we can make a number of observations. The first is that you get finite conformal transformations. You take these generators and exponentiate. Finite conformal expressions. Let's say G, and G will be a function of A, omega, lambda, and B. And again, by taking the exponential, I a mu together with the generator P mu of translations, plus I over 2 omega mu mu. M mu mu plus I B mu K mu plus I lambda T. Okay. Second point is that the generator exposed the conformal algebra. Read as follows. I am in mu and theta is theta alpha nu and mu beta plus theta mu beta and alpha nu alpha minus theta mu alpha and mu beta minus theta mu beta and mu alpha. Is with WD 0. One and mu with alpha is theta mu the alpha mu P mu minus theta alpha mu P mu I and P mu and the alpha theta alpha mu with mu minus theta alpha mu D is minus R dv and D is I dv, and then finally U a U minus I two mu D plus 2 this is the full algebra and dimensions. So this is all well and good, but it's worth asking if we've seen this kind of structure before. Okay. So it's, you know, it's a bit of a mess, if I'm honest. But it turns out that this sort of mess is in fact not entirely us, but this involves us making the appropriate identifications. So to get some insight into this algebra, let's do the following. We're going to define the following set of generators. Column L, I'm going to index them by capital letters M and N, and they're symmetric. So this means that this is minus L and M. And the following is true. M in etc. take values -1, 0, +1, 2, etc. all the way to D. Okay, so there are D plus 2 labels M, N, etc. And then, as usual, I'm going to take mu, so Greek indices, and these will run between 0, 1, to D, so D plus 1 then. Okay, so then D plus 2 here in this list, and D plus 1 in this position. That's right. I want these to go D minus D in this. So this is the usual news that we were talking about for the rest of the session. These guys are new. Okay, they take values between they take all the values that the mu of use take, and in addition, there's a -1 set of the units. Okay. And I'm going to define the L's in terms of those generators. So I'm going to take all those generators and then repackage them into the L's. That's what I'm doing. Do the following definitions. I'm going to define L mu. In other words, when these MN indices take values between 0 and D minus 1, excuse me. We're going to define these guys. And mu. Remember, I need to preserve the N's properties, but otherwise I can get it to package them in a trail. L minus 1 and D, so either M is my list. I'm going to define this to be D. Again, to be clear, this is the number of dimensions. And this is the conformal generator, notation generator. L mu and -1. And we're going to define as a half P mu plus A mu. And L mu and D, and D as an index means number of different dimensions. We're going to define as a half P mu minus A. So that captures it all, okay? So L -1 and D is D. L mu -1 is a half K mu plus K mu. L mu D is a half K mu minus K mu. And everything in between is units. Okay. You can check, you should check. Do all of them, with them. If I take eta m10, again with m and n running between -1 and d, equal to -1, sorry, diagonal -1 -1 plus 1. So there's two of these guys that are -1, and d of these guys that are +1. Then the LMNs satisfy the following algebra. I L M N L Q say is eta MQ L MP plus eta NP L MP minus eta NQ L MP minus eta NP, so eta NP L and sorry, this should be awesome. So if you remember what we've been talking about so far, this algebra is nothing but the Lorentz algebra, the algebra of the Lorentz thing that contains an n being used, only with the following L's here, right? But in D+2 dimensional spacetime. And if you recall what it means to have +2, +1, etc., this is a spacetime of D spatial dimensions and 2 times. Okay. So again, if you go back to the metric on these spacetimes, right? Okay, now this is a strictly positive, sorry, not strictly positive, this is a mostly positive metric, doesn't matter. But there's 2 times and D space dimension. That's a little bit weird. But other than that weirdness, what this is telling us is that the conformal group in d dimensions is nothing but the Lorentz group in d plus 2 dimensional space time, right? D space 2 times. Don't worry about the physics of what it means to have 2 times. It's just it's a mathematical, it's an auxiliary mathematical observation that allows us to identify the group structure of the Lorentz. Sorry, yeah. So it follows then that a formal group in d dimensional space time equal to S of 2 T, which is the Lorentz group. Plus 2. Often the weirdness of 2 times, I can identify now what the group structure of the conformal transformations are in the dimensional state. Okay, so that's all of the kind of formal mathematics that I wanted to talk about with conformal symmetries and the conformal group. And now that we've identified what the conformal group is, so you haven't done algebra. This is a set of d plus 2 by d plus 2 orthogonal matrix matrices with unit determinant. Okay. And that is the conformal group in d-dimensional space-time. Okay. So next time we're going to talk about radial quantization, and I will revise very quickly first quantization, and then we'll talk about light quantization, and eventually I will tell us about radial quantization. So it's not as trivial as basically just picking a set of coordinates in which to do calculations. It's a little bit more complex than that. And the reason for that is because I have to tell you things about what it means to take conjugates, what it means to conjugate variables, etc. in this new foliation of space time. Right? Conjugation is the operation of taking a dagger, right, and allows us to calculate probabilities, for example, and allows us to define an inner product. From the inner product, correlation functions, probability amplitude. I can give you numbers when you do experiments calculation. You're laughing because you don't have an experimental strength there. It's okay.
I don't know that are there experiments or 2 times or
No.
that's
No, but again, so 2 times in the same 1 time, but with the followers, right? So this is the point: is that the mathematical structure involves auxiliary one auxiliary time variable, but it's an auxiliary thing, it's not a different thing. Yeah. So the mathematical structure is called again. It's the same as we will learn through that time about correlation functions in these conformal theories. And typically, when you talk about correlation functions, you talk about what are called equal time correlation. So you find them the time slicing, the slicing of the space time. Okay. And there's a time ordering implied in the statement. So when I write down correlation function, I start with the readings, the operators right to the left. The ones coming more left occur later and later in time. But for example, one of the key diagnostics in quantum chaos these days called not of time order correlation, which involves actually a square of a commutator, right? So if I put the operators of the commutator two times, say it's time t is 0, time t is t, and I write out that square, and I go 0 t 0 t. Right, so that's why it's called out of time order correlation. It's not really the same as a time order correlation function where as you go from right to left, you go in increasing time. Here you go 0 t back to 0 to t. So if you think about what you're doing when you do this integral, your function of integration goes backwards in time. So you ask about how the hell can you possibly measure something that's like, and it turns out if you ask the correct physical question, then in fact you can measure something that is in this auxiliary space, measuring something in the. So the question of how you interpret the mathematics. I'll tell you all about that in the lectures to come.